Okay, let's dive in. We're moving beyond just the day-to-day, loading data, making charts. We're zooming way out today. We want to look at the really big picture, the blueprint for how an organization manages its data. Think about traditional architecture for a second, like building a house or maybe something bigger, a factory complex. Any successful building, anything that works properly, it starts with a plan, right? A really detailed blueprint. That blueprint tells you exactly how it's supposed to function, where the main supports are, how the electricity and plumbing flow, how it all serves its purpose, even like how many people the elevators can hold. Now flip that. Imagine trying to build, say, a huge modern airport with maybe 50 different teams just improvising their own sections all at once. You've got one crew deciding the baggage system goes here, another puts the main power plant there. And what you end up with is this maze. It technically stands up, maybe, but barely. Things conflict, it wastes a ton of resources, and the second you need to change one tiny thing, like adding a new check-in counter, the whole thing just seizes up. That's not building. It's just chaos, really. Chaos built on wishful thinking.
And that picture you painted, that tension between, chaos and actual coherence, that perfectly nails the data problem in so many organizations today. Data just piles up organically, fast, from every app, every merger, every time a customer clicks something. And if there's no intentional design behind it, that pile becomes, frankly, a toxic mess. We see it constantly. Organizations where, I don't know, something critical like customer lifetime value is calculated 5 different ways in 5 different places. Naturally, that leads to conflicting reports. Nobody knows which number to trust. Decisions get stalled. You get these chaotic tangles of duplicate systems, integrations that are so brittle that changing one field definition breaks something critical downstream. And maybe worst of all, this mounting technical debt that just paralyzes the organization's ability to adapt or innovate.
Right. So our mission, our deep dive today, is all about the solution to that chaos. Data architecture. This is the discipline, the practice of designing these comprehensive, hopefully future-proof frameworks for actually managing data as an asset. It's about transforming those raw, messy streams of data into what our sources call, and I like this phrase, structured, accessible, trustworthy information assets. It's moving from that messy improvisation to proper engineering.
Exactly. Data architecture is that core framework. It's the whole package.
Yeah.
The models, the policies, the rules, the standards, all the things that dictate what data you even collect in the first place, how you store it, how you arrange it, and crucially, how it integrates and flows between all your different systems,
Right.
and then ultimately how people access it and use it effectively. The architect's focus fundamentally is on the data itself. What does it mean? Where does it live? How is it governed? And how does it actually serve the business's goals, which, are always evolving?
Okay, so we've established the why. We need architecture to avoid that costly chaos. Now let's get into the how. And this is where you start to see the real sophistication of data architecture, like those building blueprints. It doesn't operate on just one level. There are multiple distinct layers of abstraction. And this is super important because it separates the business logic, what the data means, which tends to change slowly, from the technical tools, how it's stored and processed, which, let's face it, change all the time.
Yeah. This multi-level approach is really foundational. You always start at the top, the highest level, the conceptual architecture. This layer is purely about defining those high-level business things, the entities, the relationships between them. We're using the language of the business here. What is a customer to us? What's a product? How do orders relate to inventory? Absolutely zero technical jargon. No databases, no specific software mentioned, which makes it, a powerful way to communicate. Everyone gets it. Finance, marketing, legal, they can all understand and validate this level.
Okay, so that's the big picture view. Then you drop down a level.
Right, down to the logical architecture. Here we start adding structure, but we're still keeping it technology neutral. We take those conceptual things like customer and we flesh them out. What attributes does a customer have? Name, address, contact info, etc. We define the data types. Is it text, number, date? We map out the relationships more formally. Define constraints like, is a shipping address mandatory? But again, it's independent which database you'll use. The design works whether you end up using, say, a NoSQL database or a traditional relational one.
And then the final layer is where the tech actually comes in.
Exactly. That's the physical architecture. This is implementation reality, where the rubber meets the road, so to speak. This is where you map those logical designs onto specific technologies, specific systems that you've chosen. You decide, okay, our transactional order data, that's going into a partitioned PostgreSQL cluster hosted in AWS US East, and our historical customer analytics data that lives in Snowflake, and people access it through this specific API gateway. This layer deals with all the nitty-gritty technical details, performance tuning, specific security setups, storage configurations, everything.
Hold on. So the real power here, the sort of magic of this layering, is that I could completely swap out the underlying database technology, the physical layer, maybe 5 years down the line.
Yeah.
And the business folks, their understanding of what a customer fundamentally is or how orders work, that doesn't need to change at all.
Precisely. That's the whole point. The conceptual and logical layers, they serve as these stable reference points, like anchors. They maintain that consistency, that shared understanding, even while the technology landscape is churning underneath. So if, your cloud provider comes out with some amazing new storage tech, the architect just updates the physical mapping. The logical structure, the meaning of your data assets stays stable, and that massively cuts down on risk and the cost of making changes later.
Okay, that makes a lot of sense. So moving from these abstract levels to the actual components, architecture isn't just one monolithic design, is it? It's more like a puzzle with interconnected pieces. What are the key dimensions, the main parts that an architect has to design?
Yeah, you can definitely break it down into core components. The first one, and arguably the most fundamental, are the data models. These are really the intellectual bedrock. They define the entities, their attributes, how they relate to each other. Architects use different tools for this. You've got your traditional entity relationship diagrams or ERDs, great for transactional systems. And then things like dimensional models. You might hear terms like star schema or snowflake schema. These are specifically designed for fast analytical queries. But maybe the toughest and often the most valuable model is the canonical model. This is about establishing the common, standardized definition for your core business concepts across all systems. It's like the master dictionary. It ensures that when marketing talks about revenue, they mean the exact same thing, calculated the same way as the finance department. Building this common language is incredibly hard work, politically and technically, because you're often fighting against decades of different teams having their own slightly different definitions.
Right, breaking down the silos. Okay, so after the models, knowing what the data looks like next up is where it actually lives.
Exactly, the data storage architecture. Once you've defined the structure in the model, you decide where to physically put it. This means picking the right type of storage for the right type of data and its use case. You need operational databases, maybe relational ones, optimized for lots of small, fast transactions. You need data warehouses for bringing together historical data for reporting, data lakes for just dumping huge amounts of raw data in any format, maybe various caching layers to speed things up, archival storage for old stuff.
And that choice isn't purely technical, is it's very much an economic one too. You have to balance the performance needs with capacity constraints and increasingly the cloud storage costs. Like you wouldn't put super high frequency operational data in a cold storage tier designed for cheap archiving, right? Your app would grind to a halt.
Absolutely. Performance and cost are always in tension. Then, once it's stored, you need the data integration architecture. This defines how data actually moves between all these different storage systems and applications. Is it going to be traditional ETL extract, transform, load, usually done in big batches, maybe overnight? Or do you need near real-time movement? That might mean streaming data using tools like Kafka or message queues. Or perhaps systems will communicate directly through APIs, requesting data on demand. This component is like the circulatory system. It determines how timely, how consistent your data is as it flows across the entire organization.
Okay, so data moving between systems. Then there's the other end, how people actually get the data out to use it. That's the data access architecture.
Precisely.
Yeah.
The data's been modeled, stored, integrated. Now, how do consumers, analysts, data scientists, applications, business users retrieve it and work with it? This involves designing the query services, maybe the big analytics platforms, specialized environments for data science work. And a huge part of this is implementing strict governance. Who gets to see what data? Under what conditions? You need to balance giving people the flexibility they need with maintaining control and ensuring the systems can handle the load without slowing everything else down. It's a constant balancing act.
You mentioned governance there, but there's another component you said is often overlooked but critical.
Ah, yes. The one I often feel is the unsung hero or maybe the neglected child. Metadata architecture. This is all about managing the information about your data. The data's context. It includes things like schemas, usage stats, business definitions in a glossary, who owns the data, and critically, data lineage. That's the ability to track exactly where a piece of data came from, what transformations happened to it, and where it ended up.
Okay, let me try that analogy from the sources. Metadata is like the nutritional label and the cooking instructions on your food ingredients. You might have a fridge full of stuff, your data lake, but if nothing's labeled, you have no idea what's what, what's safe to use, what's gone bad, or how to actually combine it into a decent meal.
That's a perfect analogy, spot on. The crucial point here, the takeaway, is that without good, actively managed metadata, your data just becomes noise, maybe even dangerous noise. You can't trust it, you can't really use it effectively, you often can't even find what you need. It doesn't matter how fancy your database is. A technically perfect data warehouse with zero reliable lineage. It's practically useless for anything requiring trust, like regulatory reporting or serious strategic analysis.
Wow. Okay. And finally, bringing it all together under a sort of rules umbrella.
That's the data governance architecture. This isn't just one system, it's the whole framework of policies, roles, standards, and processes you need to manage data properly as a strategic asset. It covers defining data ownership, who's responsible for customer data quality, setting quality standards, defining security rules and access controls, and ensuring you can meet regulatory requirements, things like GDPR, CCPA, IIPA, whatever applies. The architect's job isn't just to know these rules exist, but to design the technical systems in a way that actually enforces them. They need to be built in, not just written down somewhere.
Okay, so those are the core components, but just listing them isn't enough, right?
Sure.
Designing them well, making them work together effectively, that requires adhering to some core principles.
Absolutely. Effective data architecture isn't just about optimizing each piece in isolation. It's about following key design principles that ensure the whole system is robust, flexible, and maybe most importantly, actually helps the business.
And the first principle you mentioned earlier is the big one, business alignment.
Yes. This has to be the driver. Every single technology choice, every architectural decision must be directly traceable back to enabling a specific business capability or goal. If the strategy is, say, personalized customer experiences, then the architecture needs to support real-time data integration and access for that. You don't choose batch processing just because it's easier. The goal isn't technical elegance for its own sake. You don't pick the newest, shiniest database just because it's cool, unless it genuinely provides the best way to achieve a measurable business outcome.
Makes sense. Keep your eye on the prize. What about the engineering side, making sure it's stable and adaptable?
Yeah, then you get into principles that promote robustness and maintainability. A big one is separation of concerns. This is all about partitioning the architecture into distinct layers or modules that handle different jobs. For example, keeping your operational systems, handling daily transactions, separate from your analytical systems, handling reporting and BI, keeping data storage separate from data processing logic. This modularity is key. It means you can change or upgrade one component without having to rip out and replace everything else.
And that modularity works best if the connections between the modules are flexible.
Exactly. That leads to the principle of loose coupling. You want to minimize the tight, direct dependencies between different applications or systems. Instead of System A needing to know the intimate internal details of System B's database, they should communicate through well-defined, standardized interfaces. Think APIs or message queues. This prevents what we call brittleness. If System B needs an internal upgrade, System A shouldn't automatically break or need immediate changes. They're loosely coupled so they can evolve independently, much more resilient.
Okay, that sounds crucial for managing change. What about ensuring the data itself is reliable?
That brings us to a cornerstone principle, the single source of truth, often abbreviated SOT. This is about establishing the authoritative source for critical data domains. For example, your CRM system is the definitive source for customer contact information. Your ERP is the source for financial ledger data. This is how you fight against having 5 different versions of the truth floating around, causing confusion and bad decisions.
Okay, but let's push on that a bit. SOT sounds great in theory, but doesn't it often become a massive bottleneck in practice? Operational teams, maybe a regional sales office, they often want their own copy of customer data locally so they can access it fast, maybe tweak it for their specific needs. How does an architect sell SOT when copying data often feels faster in the short term?
That's the classic tension. And you're right, it forces a more nuanced architectural approach. The architect doesn't sell SOT as just a rigid rule. They sell it based on reducing the cost and risk of constantly reconciling conflicting data later on. They acknowledge the need for speed. So the solution might be architectural. Maybe you architect a system that replicates the SOT data in near real time to a local read-only cache for those teams, or provide really fast, low latency API access to the central source. The key is that local copy is clearly understood and managed as a derived, controlled view of the official master data. It's not an independent source. So you protect consistency, but still address the performance need. It's about finding that balance.
Got it. A pragmatic approach. Okay, moving on. Quality and security, you mentioned embedding these.
Yes, two absolutely critical principles: data quality by design and security and privacy by design. For quality, the idea is you can't treat it as an afterthought, something you clean up later. Quality checks have to be built into the architecture from the very beginning. This means things like strict validation rules when data is first entered, using database constraints like referential integrity to prevent inconsistent relationships, building in automated monitoring to catch quality degradation early. Quality has to be structural. If your architecture allows bad data in easily, no amount of downstream effort can reliably fix it. Garbage in, garbage out, architecturally enforced.
And the same logic applies to security and privacy. Can't just bolt it on at the end.
Absolutely not, especially not today. Security and privacy must be foundational, woven through the entire architecture. We're talking about mandatory encryption, both for data moving between systems in transit and when it's stored at rest. Fine-grained access controls who can see which rows or columns, robust audit trails logging who did what when, and increasingly important techniques for data minimization, only collecting and retaining the data you absolutely need for a specific stated purpose. For example, dealing with sensitive personal data, PII, the architecture might mandate tokenization or anonymization right at the point of ingestion, so most downstream systems never even see the raw sensitive information. That drastically reduces the risk profile.
Okay, these principles provide the why and what. To make them work across big organizations with many teams, you need consistent rules of engagement.
Exactly. That's where standards come in. Standards ensure consistency, they make systems work together better, interoperability, and they create a shared understanding across different teams.
And you mentioned one earlier that sounds minor but causes major headaches.
Oh yeah, naming conventions. Standardizing how you name everything, data elements, database tables, columns, files, folders, everything. It seems trivial, right? But inconsistent, cryptic, or just plain lazy naming is a massive source of friction and confusion. If one team calls it CS Tide, another uses client identifier, and a third uses customer IDPK. Every time those systems need to talk, someone has to translate. It wastes huge amounts of time and introduces errors. A clear, enforced standard saves countless hours.
Simple but powerful. What other kinds of standards are crucial?
Data type standards are another big one, making sure the same type of information is represented consistently everywhere. Think about dates. If one system stores them as MMDYYYY, another as YYYMMTA, like ISO 8601, another as a Unix timestamp. Every time data moves, you need complex, risky conversions. Mandating a common standard format for dates, for currency codes, for country codes, for Boolean values, true, false, yes, no, 10, it just eliminates a whole class of integration problems.
And standardizing how systems actually talk to each other.
Yes, interface standards. This usually focuses on APIs, but applies to any data exchange mechanism. It means defining standard ways to structure API requests and responses, standard authentication methods, clear, predictable error handling codes, and importantly, disciplined approaches to versioning your APIs so changes don't break existing consumers without warning. When all your interfaces behave predictably, integrating a new system or application becomes much faster and cheaper. It moves from a major bespoke project towards something more like plugging things together.
So the architect has these principles and standards, but they're operating in this incredibly dynamic tech landscape. Things change constantly. They can't just pick one database vendor and call it done, right?
Not anymore, no. That leads to the concept of polyglot persistence. It's a bit of jargon, but it just means acknowledging that no single data storage technology is the best tool for every single job. A modern data architecture has to be a mix and match, a technology mosaic. The architect needs to select the right tool for the specific workload.
So understanding the different types of databases is key.
Absolutely, that's database diversity. For your core business transactions where consistency and reliability are paramount, think AC properties, you'll likely stick with traditional relational databases like SQL Server, PostgreSQL, Oracle. But if you need to run fast analytical queries over huge volumes of historical data looking for trends, then columnar databases like Redshift, BigQuery, Snowflake, ClickHouse are usually a much better fit. They store data differently, optimized for scanning and aggregating large data sets.
And there are even more specialized types.
Oh yeah, If your data is all about connections and relationships, think social networks, recommendation engines, supply chain tracking, fraud detection rings, then a graph database like Neo4j or Neptune is purpose-built for efficiently traversing those complex links. Or if you're dealing with massive streams of timestamp data, IoT sensor readings, financial market data, system monitoring logs, then a time series database like InfluxDB or TimescaleDB is optimized for handling that specific pattern of high volume writes and time-based queries. The architect needs to know the strength, weaknesses, and cost implications of all these options.
And overlaying all of this is the massive shift to the cloud. That's changed the game entirely, hasn't it?
Fundamentally, the cloud paradigm shift means architects are increasingly working with managed services. Think Amazon S3 for storage, Snowflake or BigQuery for warehousing, manage Kafka for streaming. This flips the cost model from CapEx buying big servers up front to OpEx paying for what you use, often metered by the minute or even the second.
So that changes how you design things. You're not just designing for capability, but also for cost efficiency in a much more direct way.
Exactly. It's a critical difference. In the old on-premise world, you often over-provisioned hardware because the cost was fixed once you bought it. Resources were sometimes wasted, but it didn't directly hit the monthly bill. In the cloud, poor architectural design, like running a massively inefficient query that scans terabytes when it only needed gigabytes, translates immediately into a huge bill. So cloud architecture puts a huge emphasis on efficiency and elasticity, designing systems that can scale up instantly when needed, but also scale down aggressively, even to zero when they're idle. That's very different thinking.
Okay, and tying all these diverse storage and processing systems together requires specific tools as well.
Yes, you need robust integration tools. This includes workflow orchestration platforms like Apache Airflow or Prefect to manage complex data pipelines, data movement services like Fivetran or Stitch that specialize in replicating data from source systems into warehouses or lakes. And often, powerful data transformation engines like dbt, Informatica, or Talend to clean, reshape, and combine data as it moves. These tools provide the plumbing, the monitoring, and crucially, the ability to handle errors and retries when things inevitably go wrong in a distributed system.
So it sounds like the architect's job isn't just picking the best tech, but constantly juggling competing priorities.
That's arguably the hardest part. Data architecture design is fundamentally about navigating these inherent tensions and trade-offs. There are rarely perfect, easy answers.
What's the first major tension they face?
A big one is complexity versus simplicity. If you design an architecture that tries to perfectly address every possible governance rule, integration pattern, and security requirement up front, it can become incredibly complex, hard to understand, hard to build, hard to maintain. But if you oversimplify things too much, maybe just to get a project out the door quickly, then the architecture fails to handle the actual complexity of the business. And what happens then? Teams start building their own workarounds, you get shadow IT, uncontrolled, undocumented systems popping up everywhere. Simple locally, maybe, but creating massive hidden complexity and risk for the organization as a whole.
Right, the hidden complexity. Another classic tension seems to be about control. Central versus local.
Yes, the centralization versus decentralization debate. If you centralize everything, all data goes into one giant data warehouse managed by one central team. You get great consistency, strong governance, clear ownership. It sounds ideal, but it almost always creates bottlenecks. Everyone is waiting for the central team to ingest their data, build their models, grant them access. It can slow innovation down to a crawl. On the other hand, if you let every department or team manage their own data completely independently, decentralization, they can move fast, sure, but you risk chaos. Rampant data duplication, inconsistent definitions, and no single source of truth, integration nightmares.
Is there a modern approach trying to find a middle ground here? I think I've heard the term data mesh.
Yes, data mesh is a more recent pattern trying to address exactly this tension. It advocates for domain-oriented decentralization. The idea is that specific business domains, think sales, inventory, customer support, take full ownership of their data end to end. They treat their data as a product that they serve to the rest of the organization. They're responsible for its quality, its discoverability, its security, and providing easy ways for others to consume it, often via standardized APIs.
So it pushes ownership out to the edges where the expertise lies.
Exactly. It recognizes that a central team simply can't scale to understand the nuances of every single business domain's data. However, and this is crucial, data mesh only works if it operates within strong, centrally defined architectural guardrails. The data architect's role here is to define and enforce those common standards that all domains must follow. Things like mandating specific API standards, requiring standardized metadata publishing, enforcing common security protocols, ensuring interoperability. Without those architect-enforced guardrails, data mesh just becomes a recipe for decentralized chaos, maybe even worse than before.
Okay, another unavoidable trade-off: speed versus cost.
The eternal constraint. Performance versus cost. If you want the absolute best performance sub-second query responses, zero latency data stream is usually possible, technically. But it requires premium resources, lots of processing power, high-speed storage, maybe dedicated network links. It gets expensive, fast. The architect's job is rarely to deliver the absolute fastest possible solution. It's to find the right balance point, delivering acceptable performance for the specific use case at a reasonable cost. What's acceptable varies wildly. A slight delay on a quarterly financial report might be fine. A similar delay on a real-time fraud detection system? Absolutely not. It requires constant monitoring of both performance and cost and optimizing that trade-off.
And then there's the time dimension, designing for now versus designing for later.
Right, current needs versus future flexibility. Good architecture has to solve today's problems and deliver immediate business value. You can't just build for 5 years out, but it also needs to incorporate reasonable foresight. It should anticipate likely future changes, maybe significant data volume growth, new types of analysis, potential acquisitions, without being overly rigid. The trap here is twofold. You can cripple yourself by over-engineering for purely hypothetical future scenarios that never happen, wasting time and money on complexity you don't need. But you also can't design something so brittle that the moment the business needs to pivot slightly, you're facing a massive, expensive redesign. It's about building in options and adaptability where it makes sense.
All these decisions, especially the shortcuts taken under pressure, they lead to this concept of technical debt, right? But it's not just messy code.
No, it's often architectural debt. It accumulates when you make expedient choices that solve an immediate problem but create bigger problems down the line. Think about taking a shortcut by creating dozens of direct point-to-point integrations between systems instead of building a proper integration hub or using APIs. It works now, but makes the whole system incredibly tangled and hard to change later. Or carelessly duplicating data across multiple databases just to meet a tight deadline, rather than implementing a proper SSOT approach. This debt isn't free. It accrues interest in the form of increased maintenance costs, reduced agility, and higher risk. It needs to be actively managed, tracked, and paid down through refactoring and modernization efforts.
And sometimes that debt gets so large or the original systems are so old, you're forced into legacy system modernization.
Exactly. You often have these old, maybe mainframe-based systems that hold incredibly valuable business data or logic, but they were built decades ago. They're difficult and risky to change directly. A wholesale big bang replacement is often way too risky. The chance of failure is high, and the business impact could be catastrophic. So the architect needs strategies to manage this modernization gradually, reducing risk. One common approach is using API layers to wrap the legacy system, hiding its complexity and providing a modern interface for newer applications to interact with it.
Is that where that interesting strangler fig pattern comes in?
Yes. The strangler fig pattern is a really powerful strategy for legacy modernization, named after vines that slowly grow over and eventually strangle host trees. The idea is you don't try to rip out the old legacy system all at once. Instead, you incrementally build new, modern services around the edges of the old system. Maybe you intercept calls going to the legacy system and redirect them to a new service that handles that specific piece of functionality. Or you build new features as separate microservices that call the legacy system via those APIs you built. Over time, more and more functionality is migrated out of the legacy core and into these new services. They gradually strangle the old system's responsibilities. Eventually, the legacy system might just be a data store, or maybe entirely unused. Then you can finally decommission it piece by piece without a high-risk cutover. It turns modernization from a giant leap into a series of manageable steps. So we've talked a lot about the components, principles, technologies, but we really need to focus on the who. The professional actually responsible for creating and maintaining this vision, the data architect. This human dimension is absolutely critical, and the role demands a really unique blend of skills.
Where does the architect typically start? What's their primary focus?
At their heart, the architect must be a strategic thinker. They don't jump straight into choosing databases or drawing diagrams. They start by understanding the high-level business strategy. What are the organization's goals? We want to improve customer retention by 10%. We need to launch into this new market. We have to comply with these new regulations. Their job is to translate those abstract goals into concrete architectural requirements. What data do we need? What quality level? What analytical capabilities must we build? What governance structures are essential to support that strategy?
So they're looking long-term, enterprise-wide.
Absolutely. Their focus has to be on building sustainable enterprise-wide capabilities, not just optimizing one specific project or team's immediate needs. They need foresight. They have to design for that foreseeable evolution. We talked about anticipating data growth, potential mergers, shifts in business focus. They understand that architectural principles like loose coupling, SOT endures, even when the specific technologies change underneath. They calculate the ROI of architectural investment not just on today's savings, but on enabling future agility and avoiding future crises. They see technical debt as a direct threat to that future.
Okay, so strategic vision first, but they also have to get their hands dirty with the actual design work.
Oh, definitely. They are the primary designer, modeler, and standards enforcer. They're usually responsible for designing, or at least overseeing the design of, the core enterprise data models, establishing that common business vocabulary and structure we discussed. They define the approaches for master data management. How do we ensure we have one consistent, accurate record for every customer, product, employee? And crucially, they set and enforce the architectural standards, naming conventions, data type standards, modeling patterns, security protocols.
Enforcement sounds tricky. How does that work in practice?
It's a constant balancing act. It involves doing formal design reviews, looking at what engineering teams are proposing, and ensuring it aligns with the architecture. It means providing clear guidance and education. But it also means knowing when to stand firm, to push back when a team wants to take a shortcut that violates a key principle and creates long-term risk. You have to be consistent, but also pragmatic, recognizing when there's a legitimate reason for an exception, but documenting it carefully.
It sounds like a role that requires a lot of influencing and negotiation, not just technical prowess.
Hugely so. This is often underestimated. A successful data architect needs to be an exceptional communicator and collaborator. They might spend as much or more time talking to people as they do designing systems.
Who are they communicating with?
Multiple audiences. First, executive communication is critical. They need to translate complex technical ideas, normalization, partitioning, data lineage into the language of business value. They don't talk about implementing Kafka. They talk about enabling real-time inventory updates to reduce stockouts. They need to articulate the benefits, costs, and especially the risks of architectural choices to get buy-in and funding for necessary investments, particularly preventative ones that don't have an immediate payoff.
And then collaborating with the technical teams.
Yes, deep engineering collaboration. They have to work side by side with data engineers, software developers, security analysts, infrastructure teams. They need to speak their language fluently, understand the nuances of database performance, network latency, API design, CI/CD pipelines. The key here is balancing clear direction, setting the architectural what and why, with respecting the deep implementation expertise of the engineering teams, trusting them on the how within the established guardrails.
And across different business departments, too.
Absolutely. That's the cross-functional coordination piece. Data architecture inevitably cuts across organizational silos. Finance has specific needs for data immutability and auditability. Marketing wants real-time customer behavioral data. Operations needs low-latency transactional consistency. Sales needs reliable CRM data. These needs can sometimes conflict. The architect often plays the role of diplomat and negotiator, understanding the different perspectives, finding common ground, resolving disputes over data definitions or access rights, and building consensus around an enterprise-wide approach.
And they're also heavily involved in the governance aspect we discussed earlier.
They are central to it. They act as the governance champion. They often design the data stewardship models, figuring out who in the business should be formally responsible for the quality and definition of specific data assets. They design the technical data lineage architecture, the systems and processes needed to actually track data from source to consumption. This isn't just a nice to have, it's often a regulatory requirement, like proving you can comply with data deletion requests under GDPR by tracing PII across all systems.
And connecting governance to security and metadata.
Yes. They design the security and privacy aspects of the architecture, ensuring controls like data minimization or role-based access are technically feasible and enforced. And they champion the metadata management architecture, pushing for the tools and processes needed to make data discoverable, understandable, and trustworthy through comprehensive documentation and lineage. Without good metadata, governance policies are often unenforceable.
It really sounds like a role requiring a unique mix of skills, almost contradictory skills sometimes.
It really does. That's why good data architects are so valuable and sometimes hard to find. They need to be this balanced practitioner. They need that balance between deep technical expertise, understanding the nuts and bolts of databases, cloud services, integration patterns, and a strong grasp of the business strategy, domain knowledge, and operational processes. They need to balance embracing innovation, identifying genuinely useful new technologies or approaches, with maintaining stability and avoiding chasing every new fad or hype cycle. Change needs to be deliberate and managed. And they need to balance exercising authority, enforcing standards, and saying no when necessary with acting as a mentor and coach, helping to build architectural thinking and capability across the broader engineering organization. The goal is for the architecture to be sustainable, not dependent on a single person.
Okay, so let's try and wrap this up, bring it back to the core value proposition. Data architecture, when done well, is truly the essential foundation for any organization that wants to be genuinely data-driven. It's not really about the diagrams themselves. It's about what those diagrams enable. It's about enabling core business capabilities. Good architecture makes everything else easier. It accelerates decision-making. It lowers the cost and risk of integrating new systems or data sources. It improves data quality and trust. And it helps manage compliance and security risks proactively.
And the flip side is just as important to understand. The cost of not doing this well or ignoring it altogether is immense. Poor or non-existent architecture basically guarantees that integrating anything new becomes incredibly expensive, slow, and brittle. You build up layer upon layer of technical duct tape, data silos multiply like weeds, data quality becomes unreliable, security gaps emerge, and that technical debt we talked about just keeps accumulating until the systems become fundamentally resistant to change, crippling the business's ability to adapt.
So the big strategic takeaway here seems to be that the data architect, well, maybe not the most visible person in the room, plays an absolutely crucial strategic role. Like the foundation of a building, their value is often most obvious when it's missing or when corners were cut in the design. They provide that essential strategic vision, the thoughtful design, and the necessary discipline to transform what might just be a random collection of databases and applications into a coherent, purposeful, and truly valuable information architecture for the entire enterprise.
Exactly. And maybe the final thought to leave listeners with is this. If everyone agrees that competitive advantage today relies heavily on leveraging information effectively, faster, more reliably, more innovatively than your competitors, then you have to ask yourself a hard question about your own organization. Are you treating data architecture as just a technical checklist item, something the engineers handle in the back room? Or is it recognized and invested in as the core strategic capability that it truly is? The enabler for long-term agility, innovation, and maybe even survival in your market. What architectural debt are you racking up right now, today, through shortcuts and neglect, that will fundamentally define your limits and your competitors' advantage tomorrow? Because if it takes your company 6 months to integrate a new crucial data source because your systems are a tangled mess, and your competitor can do it in 6 weeks because they invested in solid architecture, that time difference, that lost opportunity cost, that is the real measurable price of ignoring your data architecture.